Hello guys, my name is David Rodriguez and today I'll be presenting topic 7, which is electric field. First, the principles of electric field. If a body contains a specific amount of positive or negative energy, it generates an electric field around, which produces an attractive or repulsive force to the bodies nearby, so that the charged body interacts indirectly with others through the electric field. This can go from a cable connected to the current, or a Tesla coil, which is a surprise for you guys. To determine the direction of an electric field, a test charge is used. Using a positive charge body as the control charge and bringing a test charge close will indicate the direction of the electric field. If the force over a test charge is positive, is of attraction, then the force points into the direction of the electric field. If the force over a test charge is negative, is of repulsion, then the force points into the opposite direction of the electric field. Now, what are the electric field lines? Field lines provide a graphic representation of electric fields. The field lines of a positive charge will go outwards, and the field lines of the negative charge will go inwards. Now, this is a very important thing you need to understand in order to make the experiment later. A point charge produces an electric field in every point in space. The intensity of an electric field is related to the density of the fine lines. The more fine lines are in the point, the more intense is the field. The intensity of the field decreases as the distance increases, right? So what this means is, if the objects are close, there are a lot of lines connecting them. If they pull away, the lines break and there are only few lines connecting them. Now I'm going to explain the scalar form of the electric field. The electric field is a vector because it has a magnitude and a direction. The scalar value, or the magnitude of the vector, can be calculated by the following formula. E is equal to the magnitude of the electric field, which is the electric force between the charges divided by the test charge. By substituting Coulomb's law in the equation in the previous slide, we get the formula to calculate the electric field of a charge. Again, E is the field magnitude. K is going to be the proportionality constant, which the value is right here. The Q is going to be the charge divided by the distance from Q to any point in space, which is going to be the, let's say, R2 square. Now, the vector form of the electric field. Sometimes it is useful to know the components of an electric field at a given point in space. Thus, we can use the unit vector to find the magnitude, components, and direction of the field. Again, E is for the electric field vector. F is going to be the force of attraction or repulsion. Q is going to be the charge. So you need to divide the force by the charge and multiply it by the unit vector. So again, when substituting Coulomb's law in the previous formula, you obtain the following expression, which is again electric field equals the proportionality constant, which is K. You need to multiply that by the charge divided by the distance from Q to any point in space. Multiply that by the unit vector. Now, to know where is the vector unit that gives the vector direction, you need to use the following formula, where X and Y are the rectangular coordinates of the points in space at which you are calculating the electric field. If the point is in a three-dimensional space, then you add the letter C. Now I'm going to explain the electric field superposition principle. The electric field superposition principle states that the electric field of any charge combination is the vector sum of all the fields produced by individual charges. And we can express the following with this formula, where E, again, is the electric field vector equals the force vector divided by the charge. And then you add all the fields stated in the formula. They can be as many as you want. If you want to calculate the electric field produced by a continuous charge distribution, divide the distributions in smaller elements and calculate the field vector produced by each one. Then perform the vector addition of all the components. As I said, first you do the division and then you do the adding of all the fields. For example of the superposition principle is this image, right? Here's the positive charge, the negative charge, and all the electric fields, right? So this is number one, the one you're going to add using the anterior formula, number two, and number three. At point P, the electric field produced by the charges has a resultant of the electric field vector that can be calculated with the superposition principle performing the vector sum, right? Which is the first field plus the second field plus the third field. Simple. To calculate the resultant field, you need to find the rectangular components of the vectors, and by using the unit vector equation of or trigonometry, and then add them. So you do the sum of all the vectors, right? These one are the x vectors. You add them to the y vectors, and if it's three-dimensional, you use the letter C. Once you have the components to calculate the magnitude of the resultant field, you need to apply the next equation, right? So the electric field superposition principle is going to be here. You need to do the square root of the x vectors to the square, the y vectors to the square, plus the z vectors to the square. Now it's time for the experiment. As you can see, here's the little spoiler, the Tesla coil.
Now guys, it's time for the experiment. The sad thing about the electric field is that you cannot see it. There's no way you can see it. You need something, a tool, an invention to see it. In this case, the tool I'll be using is the Tesla coil. Consists of a small coil and a big coil, which is down here. I know they look flipped, they are not. So what is the Tesla coil doing here? It is going to exert positive energy, right? Positive energy through the air, and that's supposed by all the things I explained earlier to attract negative energy or a negative body, right? In this case, the negative body is going to be the argon gas that is inside the light bulb, right? So it's close. As I explained, there are many connections here, from positive to negative, right? Positive to negative, positive to negative, positive to negative, right? They are connected. Why does this happen? Because, as we all know, all the elements have electrons and protons. Protons are positive, we don't need them. Electrons, negative. So, the Tesla coil, the positive energy of the Tesla coil is going to pull the electrons, making a chemical reaction that is going to light up the bulb. But as I move it far from the coil, the connections break, and suddenly there's just one connection left until there's nothing left. They disconnect. I pull it back in. They're supposed to connect. Wait a minute. Damn. They connected again. So, as you can see the field, you can physically see the field, right? Here the field ends. So now what happens when the positive charge goes to ground? In this case, ground is myself. My finger, ground. Energy goes to me. So there's no energy to light up the bulb. Lights up again. Now I'm going to use another bulb. I put it in between. It's supposed to pull all the energy from this bulb. It pulled the majority, right? And move it outward. It stops here. It was supposed to stop there, right? It's because this little bulb is attracting all the positive energy. And that's all. I hope you like the experiment and you understand now something about electric fields.